Okay, so this week, Aleksey and I are reading this paper from Hot Storage 25, which happened, I think, July, right, Aleksey?
Yeah, I think it was right like after OSDI, and we were
In
kind of
Boston.
oblivious to that.
Okay. And this is a systems paper. Can a client, and hot storage is storage, and this is about disaggregated storage. Can a client server cache Tango? Okay. Can a client server cache Tango? Reminds me of the movie about Tango and cache, but this is like, can a client server cache Tango? Okay, the client and server does Tango means dance between the client and server's cache. Can this accelerate disaggregated storage? So the rules are like we didn't read this paper. Alexa chose this paper for this week. Maybe next week I get to choose the paper, and we do this, on the fly, off the cuff, reading of the paper together, trying to make sense of the paper as much as we can. We will try to limit ourselves to 2 hours. The goal is again to show how distributed systems experts, researchers in the field read papers to make sense of them. What is the thought process when we read papers, and sometimes what's the gaps between what the right authors think that they are communicating and what the readers get from the communication. So this is what we are gonna do. Hold on, let me set up maybe this. Okay, I'll get this window to my laptop screen. Okay, let's go. I'll try to read and annotate and
Yep.
okay, can a client server cache Tango? This is hard to parse. Okay, can a client server?
Well, I think just from the title, right?
Mhm.
They will have a cache on the client side and the server side of some
Yes,
disaggregated storage.
yes, yes. Well, all I'm saying is this sentence is hard to parse. Can a client server cache Tango? Cache Tango? Accelerate. Just say dance, maybe. Well, maybe that's even harder. Okay, let's get to it. Disaggregated storage architectures have become a critical component in modern data centers. That's correct. Spanner is disaggregated. If you didn't,
Spanner is it?
it is. It is. That's why I mentioned. That's what the guys at Google said. It has been disaggregated for a long time. And most databases are going that route now. So it's a thing. Okay. I mean, yeah, there was a discussion about this in SIGMOD 2022, and then the AWS guys were saying that, there is no need to discuss. This is already happening. This is the cloud reality. I mean, we need to disaggregate for economy of scale reasons and have compute and storage separate. That saves a lot of money and allows us to scale them independently. That's already happening. No need to
Well,
discuss.
I do want to point out though
Mhm.
this Open Aurora paper, right? Like
Mhm.
some researchers trying to implement the Aurora AWS Aurora like disaggregated architecture, but like open source.
Mhm. Mhm. Yeah,
Right?
I remember
And
that.
yeah, and in that paper, all of their attempts had like significantly worse performance than just the
Yeah,
baseline system, right? So,
yeah,
I do take some of this like, we are disaggregated type of
yeah,
stuff as a grain of salt, right?
yeah, yeah,
Maybe
but
they're just,
yeah,
writing data to you know, like a storage subsystem like I don't know, EBS is not being disaggregated, even though it does provide you kind of an independent layer, right?
yeah,
So
yeah, yeah. I mean, the thing is follow the money. This is this is the economically viable thing. This is how to scale them separately, storage nodes, and you don't replace storage node or you don't replace a server just because the storage is gone and you are not using the compute enough, or you don't replace um,
okay,
the node just because
counterpoint.
compute is too overloaded, but there is still storage.
Counterpoint, Murat. Like, you follow there is a good like incentive, right? Separate the compute resources, storage resources, scale them separately, blah blah
Yeah.
blah. But when you have that disaggregation, right, you
Mhm.
introduce like all this added complexity,
Oh
right?
yeah, no.
And you introduce the
No.
added latencies, right? So things
Yeah.
become slower, and you
Yeah.
counteract those added latencies with caches, which kind
Yes.
of the reason why I picked this paper, right? I
Yes.
think that's what the problem we're going to
Yes.
try to
Yes, no,
solve.
I think we are in
Now,
violent agreement. The performance can suck, but it's fixable. And see, this is an attempt. You
no,
always
no, no.
follow the
Look,
money. Mhm.
but now you are, by disaggregating the compute and storage, you actually placing more dependency on aggregation of compute and RAM and memory, because now you have need to have bigger caches. So now you need to provision more RAM for your compute. So
Hmm.
like.
Hmm. Okay, we are doing terrible on time. When did we start? Like 40. Okay, first sentence gone. Let's keep going. However, disaggregation introduces performance challenges. Yes. Okay. Particularly due to overhead of remote storage access. Yes. We first conduct a detailed end-to-end analysis of existing caching strategies and identify the critical issues, such as high server resource consumption, data duplication, lack of fair server resources scheduling, inefficient eviction and prefetching policies. Caching is hard, man, especially, yeah. Like a lot of systems issues here. Okay, to address
Yeah.
these limitations, we present the preliminary design of Orca cache. Okay, this paper is from Rutgers University and Samsung. Is this Samsung person maybe was at Rutgers and moved there or something? I don't know the backstory on this, or
Yeah.
maybe this is a collaboration. Okay. To address these limitations, we present the preliminary design of Orca cache. Okay. An orchestrate. Okay. Oh God, what a pun. Orca cache, an orchestrated unified caching framework.
Yeah.
Orca is an orchestrated, not the whale. Unified caching framework that coordinates between clients and storage servers. Orca cache aims to carefully switch cache indexing to clients. Okay. Shift cache indexing to clients by exposing a global cache view with an aim to reduce server CPU usage. Okay, if you shift the cache indexing to clients, you may reduce the server CPU usage and duplication of data across caches, but you probably open up a lot of cans of worms, and let's try to figure out what those are. Orca cache also aims to improve cache efficiency, adaptiveness, and fairness across servers and clients. Last time we skipped to conclusion. Let's skip to conclusion to see that concluding remark, one paragraph or so, whatever that is, and then I'll give it to you to read the introduction. And this is, again, a short paper, right? Hot storage, hot bus.
Yeah.
Okay,
Yeah.
7 pages. Okay, this is, and the last page is probably references. Yes, the conclusion is one paragraph, and this is saying that NSF Chameleon Cloud tanking it
Eh, Yeah,
tanking.
the conclusion says nothing, Murat.
Okay, in this paper, we explore and analyze the benefits and implications of different caching strategies. So present the preliminary design of Orca cache that addresses the key limitations of in our ongoing work, we plan to address the challenges mentioned above and perform a detailed evaluation of. Yeah, the conclusion doesn't say much. There is a figure 2, figure 1, the usual stuff. Okay, Aleksey, take it off with the introduction. Maybe first one.
Yeah, so disaggregated storage architectures have emerged as foundational design principles for modern data centers. A bunch of references, they actually might be interesting to look at. By physically decoupling compute and storage resources, can you scroll up?
Oh, yeah. Shall we check the references? It said that, what did it say? Okay, let me check on my other screen. 6, 7, 15, 18, 27. 6, 7. Okay. 6, a big one. Okay, empowering Azure storage with RDMA, of course. Yeah. Is this the which year? 23. Okay. RDMA, okay. 7. Hailstorm, disaggregated compute and storage for distributed LSM-based database. Okay, sounds interesting. 2020, I didn't know. 15, Anna Kilimovic, yeah, flash storage disaggregation. And 18, disaggregated compute resources and storage service in storage system, a patent, really? And Jesus, 27. Bernstein, DDS, DPU optimized disaggregated storage. What is DPU?
That's network.
Okay. Okay, Aleksey, here you go.
Yeah, DPU stands for data processing unit, essentially, fancy networker.
Okay, interconnecting them over high-speed network disaggregation offers critical advantages. Independent scaling
Advantages.
of resources, improved fault isolation, simplified maintenance, and better hardware utilization. Aleksey would have with these.
Yeah, these benefits make disaggregated storage attractive to cloud providers, enterprise systems, and large-scale machine learning, of course. However, disaggregation
What does
also.
machine learning have to do with this?
Hey, you have to
Are they
include machine
writing
learning.
this to be trendy?
Yeah, you have to include machine learning. Okay, machine learning consumes a lot of data. Data comes from databases. Databases are
Oh, this is
disaggregated.
like the big data trend in the 2010s. You have to mention big data. Okay.
Yeah.
Or 2000s,
so
even 2000s. Okay.
disaggregation also introduces new performance and efficiency challenges, most notably the latency and bandwidth costs of accessing remote storage across the network. Right?
Yeah.
To mitigate this cost, systems often employ caching mechanisms that store frequently accessed data in the memory of compute node. Compute
Yeah.
node is the client
Yeah.
here, right? Or storage node, the server. We categorize the existing disaggregated storage caching mechanisms into 3 broad categories. Client
Oh,
local
okay. This
caching.
is important. Like
Yeah. Like
when we say client is the compute node, and when we say server, it's the storage node. Okay.
in my mind, client was like an actual like client of the compute
Yeah.
node,
Yeah,
right? Like client
that's
of the database.
exactly. That's what I was thinking.
Yeah.
But no, they are saying client is the compute node and server is the storage node. Okay, good to know.
Yeah. So I mean, from that perspective, things start to make a lot more sense. Like client local caching. Yeah, you want to have like cache on
Of course.
the compute node, right? Because
Of
the
course.
cache on the server, you still have the network, right? So like,
Mm.
you know,
So maybe
yeah.
this is not that interesting paper. Let's keep reading.
Well, let's see. So they have 3 categories of caches, right? Client local, server only, and independent client server caching, which like I don't know what that means.
Yeah.
So first for client local
I mean,
caching,
they shouldn't be independent. Like they should be coordinated or orchestrated as an Orca cache. Independent? Well, I don't know. Okay. Okay, let's read.
for client local caching, wherein each compute node maintains its own cache,
Yeah,
OS page cache or user space buffers to reduce the need for repeated
of
remote
course.
fetches. The design is used in technologies like NVMe over Fabric, which allows clients to access remote logged devices as if they were locally attached. So
Mhm.
they are like really talking about like a much lower level,
Yeah.
closer to hardware caching than
Mm.
um, I guess the kind of caching that software systems people would imagine. But okay.
Yeah.
In such systems, clients mount traditional filed systems directly on remote storage, relying entirely on local memory for cache. Okay. My big question here is this really like a this like aggregation?
What do you mean? Are you saying
Uh,
this looks more like file systems
well,
work
it's
than
well, no,
disaggregation?
look, uh, I guess disaggregated storage, yes, not disaggregated database, right? So
Hmm, hmm,
we have a bias coming into this paper,
hmm, hmm.
thinking about databases,
But
and you know,
they never
not
said
yeah,
database. They said
exactly,
disaggregated storage.
exactly, but you know, okay,
Okay,
what
no,
I'm saying is
I see what you're saying. Maybe this is
I
simpler
have a
than we thought.
bias, right?
Yeah, I think we looked at this by saying or hoping this would be disaggregated database paper because we are also trying to think of those problems, but maybe this is simple than that. Okay,
Yeah, but well, you know, if you have a file system, right?
yeah.
Like you can run whatever you want on this file system, right? And whether this file system is on your local disk or remote disk, you know, from the logical perspective, right, of like the
Mm,
software you run on top of these file systems, it doesn't matter. Like what changes, of course, are the latencies, right? So
mm,
having that file system is local cache, you know,
mm,
I think it's still also like similar problems that you know they need to solve
mm.
here as you know we would in like disaggregated
Yeah.
databases, but you know if you solve it at the file system level, you're solving it like kind of a general purpose, right?
Mm,
Because like whatever you put on this you know file system, you know what applications interact with this file system, it kind of becomes relevant. It's more general purpose, whereas you know in a disaggregated
mm,
database that would be more uh,
mm,
specific, right? More purpose-built kind of
mhm, mhm.
solution.
Yeah, yeah.
Okay. While client local caching performs well in many workloads, figure 1b, that would be actually interesting to see what workloads they look at. It overlooks the substantial DRAM available on storage servers, okay?
Mm.
Often tens or hundreds of gigabytes.
Okay, is this what kind of storage servers does this guy say? 14.
Yeah, so again, like to me, it would be interesting if I'm like when I imagine a storage server, right? Like I imagine a machine that has, I don't know, 16, 32, like really big number of SSDs, right?
Huawei, okay.
If
Plus
you have like
storage, okay. Mhm.
if you have this like if you have like storage machine with this like
Yeah.
huge amount of SSDs, right?
Hmm.
10 or even 100 gigabytes, you know, when
Yeah.
you're like really talking about maybe you know terabytes, hundreds of terabytes at least, if not more, or even yeah, you know, data like
Yeah.
no,
Okay.
that may be like drop of water in the ocean. But yeah. In this model, the server memory remains unused, forcing every cache miss to traverse the network to reach the storage device.
What? What is it?
Okay, so this loses me
Oh,
because
I
if
mean,
you
why are you not using the cache at the storage?
no, but like
I mean, if
if
you
the
put
server
it
memory
alone,
is unused and you have a cache missed because of the client local, you're going to traverse the network anyway, regardless of whether it's in the server's memory or storage.
yeah,
So that
yeah,
sentence doesn't make sense to me.
yeah. No, I see. I think maybe they are saying that you even go to the storage device, not to the cache of the storage device, but you are right. I mean, after you go
No,
to the network, why does it matter? And my point was actually this is an orthogonal problem. Storage could still have its cache, but I guess you are saying that, oh, due to the cache at the client, i.e., the compute node, the storage cache may not be hot and you read from the storage, but the network
well, I didn't
volume
say
should
that,
be
right?
same, not the, yeah,
This paragraph talks strictly about client local caching. So they assume that there is only
sure,
cache on the
sure.
compute side, but the
Sure.
memory, the RAM on the
Oh, okay.
storage is not
Maybe it
used.
is saying a very obvious thing, and
Yeah,
that's why
yeah,
we are confused. Okay.
yeah. But what confused me is that sentence. In this model, the server memory remains
Of
unused.
course.
True, forcing every cache miss
Ah.
to traverse the network. Well, yeah, if
Mm.
you have a cache miss from the local cache on the
Yeah.
compute, you will go to the network regardless of whether you use the server RAM for caching or not.
Yeah. No, makes sense. Are
Right?
they thinking of
I
maybe
don't know.
server cache? What? Yeah.
Yeah.
It doesn't make sense.
This adds latency, increases network traffic, and amplifies storage I/O load. So the last one, storage I/O load, sure, if you don't have it in storage RAM, you go to disk. Yeah. The problem is especially acute in write-heavy workloads, where client memory must buffer writes before flushing. Once full, the client stalls until space is freed, despite idle server memory that could absorb these bursts. Okay.
Okay. It's just saying that, yeah, if the client memory is full, it needs to flush it to the server back.
So I think what they're saying is like if you're doing a lot of writes, right? You're
Yeah.
buffering things on the client, and
Mhm.
then you flush, and when that flush happens, a buffer has to go over the network to the storage server. But if
Yeah,
you have some kind of synergy between the two, right? As you're
of course.
buffering on the client, you can already start sending the data and buffer it on the
Yeah.
server side. So, you
Yeah.
will actually reduce the latency in that way, I think,
Yeah.
right? Because you're not waiting until the
Mhm.
buffer is full. You kind of streaming that buffer over to the server side and using the server's RAM at this point.
Yeah.
So maybe that's what they meant by
Mhm.
uh, uh, uh,
Yeah.
adds latency. I mean, yeah.
Okay.
The second one is the server-only caching, right? So that's the opposite. You don't have any cache on the compute. All the
Mhm.
cache is over the network on the storage side, right?
Mhm.
Uh, Deploys the cache solely on the server node, typically implemented using in-memory stores like memcached or Redis. While this helps reduce storage I/O, it suffers from high network latency as each client request must be must be forwarded to the server through the network.
Yeah.
Additionally, the server experiences significant CPU and memory consumption as it manages metadata, indexing, and caching policies of thousands of clients.
Okay, let me read this one. Third, independent client cache. Client server caching refers to independently managed client and server caches. As if, where both ends of the storage stack, client and server, maintain their own caches. The goal is to combine the benefits of local access at the client with the additional memory capacity at the server. However, in practice, client and server caches are typically managed independently. For instance, in production systems like Amazon S3 and Azure Blob Storage, caching is heavily used but entirely opaque to clients. What do you define as clients? The compute? There is no, I mean, the server, okay, I see. The server, even it's part of Amazon, maybe it's not integrated design. Even the compute is in Amazon, is not integrated design. Maybe the server might use an object store cache, such as memcached, while the client uses the OS page cache or application level buffers. I think this might be important. There is some impedance mismatch is what they are going to say, I guess. Therefore, clients cannot observe cache contents, eviction, prefetching policies, or receiving feedback on cache effectiveness. This limits the ability to coordinate caching decisions across client and server. Okay, this is, I guess, they are close to
Yeah.
making their point.
Mhm.
Okay.
This independence leads to several problems, and they list them, right? So one, similarly to server-only caching, it also suffers high CPU and memory consumption on the server, as they also must manage metadata, indexing structures, and policies for thousands of clients. Two, frequently accessed data is often duplicated across client and server caches, and they refer to table 1.
This is like requirements, system
Yeah,
requirements.
yeah.
Now they
Leading,
are listing.
yeah.
Mhm.
Leading to redundant caching and waste system memory because each cache operates independently using its own eviction and prefetching policies without knowledge of other state. The server may evict hot data still needed by the client or
But like they made the point about flushing. If it is also on the server cache, it would be easier to flush maybe because
Oh, no, I made that point, right?
Mhm.
Not them.
Right? I mean, n- maybe parts would be changed, but
Yeah,
then you only send the change parts, and it would be easier to update on the server side. Okay, let's keep going.
yeah. So, uh, oh, the list keeps going, right? So the server may evict hot data still needed by the client or prefetch data already present in the client, reducing overall caching effectiveness. 3, independent client server caching lacks a fair server resource scheduling mechanism, leading to significant unfairness across clients. Okay, I need to parse that one.
Like fairness point.
Yeah,
What
yeah,
that
yeah,
point is, we are going to see, I
yeah.
guess, in figure one. There
Yeah,
they alluded to figure 1b before, now figure 1c, and also table 1.
yeah.
Okay, we can look at the
Uh,
figures after this paragraph.
mhm.
Since server resources, including CPU, memory, and storage, are shared among all clients, some clients can monopolize these resources, resulting in right.
Yeah,
So
yeah. Yeah, so they're talking about like starvation and things like that.
yeah, fair server resource
Yeah,
scheduling.
yeah.
Okay, like one client should not monopolize the server resource scheduling. Okay. Additional, this design lacks an effective eviction and prefetching strategy. So they are going to say integrated,
Mhm.
coordinated design is important. As the client and server each employ their own independent policies. Um, Okay, I hope this lack of coordination significantly increases cache misses, and under certain workloads can even perform worse than client local cache. Oh, that's interesting. So you see what's going on? They are building the tension.
Mhm.
They are building up the problem before they solve. And this is common strategy to build up tension, build up tension. Now they are saying our contributions as we imagine that to be. But here's the thing, like this client server coordination, I mean server client coordination, I this should be not with respect to just one client, right? So S3, it doesn't have a single client in Amazon, multiple clients. So I hope they give us a framework where this is not just one specific type of client, let's say, I don't know, Aurora or this or
Yeah.
that
But
type
again,
of
for
S3,
the
but also works across different clients like, okay,
for them
analytical
client,
database, OLTP database, etc.
yeah, but that's not the point, right? For them,
Oh
client
yeah,
is the compute node of the
yeah.
system. So, imagine S3 as
So it's
collection of
basically single
yeah,
system. It's
yes.
not reusable across. Okay.
Yes, it's like you as a client of
Yeah.
S3, as a user of S3, you will interact with the compute of S3, and that compute or set of compute nodes are the
Hmm.
clients that then connect to the storage, right? So I can
Okay.
have 10 or 100 or 1,000 of this, S3, let's say, computes, right? That all at some point will need to fetch data from the same, let's say, server,
This
storage
is
server.
solving a simple problem, but you can say, why can't the client be a database service using the storage as the server?
Yeah, maybe if we
Could
have
be.
time for discussion later, then
It could be.
I have some thoughts on that.
Okay, let's look at figure
Yeah.
1 and table 1. Okay, this is table 1, doesn't mean much to me. Independent client server caching, data duplication. Okay, they made one point about it and it comes later. Figure 1, analysis of existing caching strategy in performance, resource usage, and fairness. Again, too early for us to make sense, but okay.
Well, they refer to them, right? So,
Yeah,
client like figure B, it's these three types of caching
yeah.
strategies, right? Client local, server only, independent client server, and
Mm.
it's a throughput, right, of something. I wish the description was a little bit more descriptive, right? But
And fairness, who knows? Okay, per client throughput.
yeah, so I
Mm.
guess what they want to show us here is that there are a couple of clients who get a lot more of stuff done than the other clients, right? So it's not fair, but for the fairness of
Oh, okay.
for, for,
And
for the
yeah,
fairness of this unfairness, right?
Right, but this is existing caching strategy.
Yeah.
They will later show a
Yeah.
figure where they beat the crap out of this one with
Or maybe not. Well, we don't know.
okay, or maybe not. I don't see another figure. Okay, this is a position
Yeah.
paper. They don't have another
Yeah.
figure. They don't have a
But
result.
I have a complaint about fairness though.
Yeah.
Again, maybe they will explain. I hope they explain this more when they
Mhm.
talk about this, like in their findings, right?
Okay.
But
Yeah.
just because some client gets more throughput, it doesn't mean it's
Mhm.
unfair. It may be
Mhm.
a higher priority client, for example, right?
Mhm.
So, uh, uh, like if you have any
Mhm.
kind of priority system, right? That's is something to be
Yeah.
expected.
Okay. Contributions. We conduct a detailed analysis of three existing designs to identify their limitations, including high CPU and memory consumption, data duplication, lack of server resource scheduling, and inefficient eviction and prefetching. Section 3. Okay, that's figure 1. To
Mhm.
address these limitations, we propose our preliminary design of Orca Cache, an orchestrated, unified caching framework that coordinates between compute nodes and storage servers to minimize the storage server resource consumption and enables adaptive server resource scheduling, efficient eviction, and parallel prefetching. Details in section 4, and that's the whole paper. There is no evaluation because this is just a prototype design proposed.
Mhm.
And if we look at figure 2, do we make sense of it? Is the upper thing clients or cache? Namespace, uh, one cache.
Yeah, let's get back to it, once we
Okay,
get to,
let's get back to
yeah.
this later. Okay, Yuri,
So
we are at
section 2 is
okay.
background, right?
Oh, we have another paragraph before we go to
Oh, yeah. Orca Cache strategically shifts part of the caching and indexing responsibilities to the client, reducing server CPU utilization while enabling a global cache view on the client side to minimize data duplication by retaining only essential data. Okay. Additionally, Orca Cache maintains lightweight cache memory allocator and continuously monitors server resource usage, including CPU, memory, and storage bandwidth, to support adaptive and fair resource allocation based on runtime information. I think that paragraph refers to the server cache
yeah,
part. Yeah,
yes,
yeah,
definitely. Yeah.
yeah. And finally, Orca Cache introduces flexible cache eviction based on the global
Policy
cache
based.
awareness.
What?
Finally, Orca Cache introduces a flexible cache eviction policy based, I think they're supposed to say on the global cache awareness or something like that,
Mhm.
and also supports the concurrent prefetching across client and server. Orca
Mm.
Cache can improve overall cache efficiency, resource allocation fairness, and reduce server CPU usage.
Mhm.
In future work, we plan to conduct a detailed evaluation. Okay.
Okay. There is no mention about Samsung. The Samsung thing could be one of them moving to Samsung.
She is a staff engineer, so it looks like she's
Oh,
been at Samsung for quite some time,
okay. So it's
or
not.
at least in industry for quite some time.
It's Samsung doing something with this. Could be maybe joint research or something, but it wasn't mentioned in the acknowledgement.
It may be as simple as they got the drives from Samsung.
Hmm. No, they said they thanked NSF Chameleon testbed, so I don't know. Okay, background and related work. We present an overview of various caching approaches in disaggregated storage and related work on prior systems. Okay, we will skip most of this, I think. Let's skip quickly.
Let's glance through it. Disaggregated storage. I think these are the same citations we already looked at, so we can move on
Yes.
that.
Okay. No, I don't. This paragraph doesn't have new information. Client local caching, you already told us about it.
Yeah, they kind of repeat client local caching, then server only caching, independent client caching. It's almost a repetition, it looks like.
It's repetition.
Hmm.
Server only caching. Okay, repetition with uncached. Independent client server. Okay, this is redundant. Okay.
There is 2.2 related work, couple paragraphs.
Hold on. Yeah, this is redundant. Related work. Darlin et al. Introduced the concept of cooperative caching in distributed file systems. This is more about distributed file systems than we thought it would be. Okay, where
Yeah,
both
well,
client and server memory are used as cache accessible to clients. They evaluate several algorithms for cooperative caching with n chance forwarding outperforming the others. Do you know about n chance forwarding?
nope.
Interesting. Let's look at 8. Looks like something we should know about. At least what it is about. David Patterson, Mike Darlin, cooperative caching, and what is this? Is this a book? Is this a what? What is ND? What is ND? What is ND? In in oops. What is ND in references?
So this is the paper from 1994. OSDI.
No date. But what
Oh,
is like
yeah, OSDI 1994.
how do you not give a reference? Like what? OSDI 94, a very
Yep.
old work. I thought it would be, but this is even older than I thought. Yeah, maybe not. Okay, let's see. Wow. And like this is not a this reference is missing.
It's not the only one. Like number 4 and number 5, like a lot of them are no date. Number 22.
But this is
Yeah.
no
Yeah.
date and no conference. Use Google. Okay. I mean, okay, I mean, why are we talking about this work? Are we saying that this is the same problem, different problem? There has been a lot of work on distributed file systems, right? Right.
Mhm.
Uh, and this is invoking it, but is this same problem, different problem? Any commentary on that? Let's keep reading. By migrating clean pages between nodes, GMS, this can,
That's it. That's another citation, number 10.
yeah, number 10.
Yeah.
Should I keep look at it? Okay.
I can give it a look quickly and just tell you. It's a 1995 paper.
Very old. Okay. Wow. Okay. So here is what I'm going to write. I'm going to say like what's the point of this related work?
Yeah.
They
The
should be
number tw number tw number
more
20.
explicit. Are is um is this the same problem? Related problem?
I mean, if you go back to the description of 8, right? Yeah, like to me, it is related problem, but maybe solved in a slightly different way, right? Instead
Maybe
of
it's the same problem. I mean, they are saying like, okay, storage is serving and client
yeah,
is compute. Why is it not
yeah,
a distributed file system problem again? And then what is new here? Okay.
yeah.
Sarkar 20 et al. Propose a hint-based caching system to reduce. I'm going to be disappointed if this is also 90.
It's 96, 96.
Jesus, man.
They're moving up.
94, 96.
94, 95, 96.
Okay, 94, 95, 96 references.
Yeah. Well, the last
More
one, OmniCache, is new. That's 24, I think.
the most closely related work, OmniCache. Let's take a look at this. Target smart storage devices. Okay, maybe the difference is smart storage, and they are revisiting the problem with modern hardware. It
Yeah,
introduced.
but the introduction didn't mention anything about smart
Nope,
storage.
it
So,
didn't. It
yeah.
introduced post-managed cache index. While it improves performance by leveraging storage site memory, it is limited to single machine deployments without the constraint of network latency. Okay, OmniCache. Did I hear about this?
No, we heard about OmniPaxos.
Oh, maybe that's okay.
I was looking this up as well. Like, sounds,
Yeah.
yeah, but no.
Okay. This is a fast
Mhm.
Usex conference on file and storage technology. We haven't heard about this, and you are saying 2024.
Yeah,
Okay.
yeah, it's a CXL paper. So
Okay. Yeah, but when you write related work, you should say like not just list the papers, but say how they relate and how are you comparing, contrasting. Um,
yeah.
Without comparing, contrasting, there is no point to.
And especially in a paper like this, where there is like no evaluation with the state of the
Yeah.
art,
I
right?
mean,
So
like, is this the same problem with distributed file systems? Okay, motivation. To
yeah.
better, I mean, I'm motivated. Like, I don't need more motivation. I just like to understand the technical parts of
Well, I think this
the
is the meat
problem.
of the paper. Like that's the findings that they talk about.
No, remember, this is just saying, oh, we compare the three models in section 3. They are going to
I-
compare the three models here. But
Yeah,
I want to see, okay, maybe.
that's the motivation for Orca cache, right?
But
So
no,
so so
but
the
this is still going to repeat the same thing about client only, storage only.
yeah, but
Right?
this is where
Yeah.
they do the experiments.
Okay, okay. Like, okay, experiments are good, but you can also qualitatively tell me, which you did actually, about the problem. Now I'm going to see it again. I think I want to see solutions, and I think I want to
No, no,
see
no.
the
Look. The
placement,
work. No, no, Murat. Look, it's a gem here.
contextualization of this with respect to
It,
previous work. New, I think I'm more algorithmically.
no, it's a gem here. Workload. Read the workload to emulate the machine learning applications.
Oh, geez. Okay.
Right? So they are looking at the storage,
Hmm.
for machine learning, of
Wow.
course. Um, where each thread loads separate chunks of data for training, we run, so they have
So
some,
it wasn't just lip service, I guess. I hope. Okay. Okay. We run 32 threads concurrently, each accessing a private 4 GB file with cache warm-up. Yeah, modern workload. Let's say modern workload. This is not the
yeah.
traditional distributed file system workload. Okay. For client local caching and server only caching, we set the client or server cache size to 36 GB. Yeah, and modern hardware, a lot changed.
So big question here, like 36 gigabyte. If I'm doing client local caching and I have 10 clients, I have 360 gigabytes of cache, right? If I have a server only cache and I have 36 gigabytes, I have 36 gigabytes of cache. Like the numbers are not necessarily comparable.
No, I didn't follow you.
What's the point of disaggregated storage?
Hmm.
You have multiple computes, multiple storage,
Mhm.
right? So if I have 10 compute nodes interacting with my storage system, I have 10 times 36 gigabytes of cache.
Mm-hmm. Yeah.
Right. Each of my compute nodes, if they have different interaction
Mm-hmm.
patterns, right? They
Yeah.
have different caches. You can have up to 36 times 10, if I have 10
Yeah.
compute node of
Okay.
cache. If you
Yeah.
go with the server side, server only caching, it's 36 for all of them, for 10 or 100. It doesn't matter how many,
Mm.
right? That alone can be a big, big, big difference
Of course. No.
in cache hits and cache misses.
Of course. Yeah. 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 For independent client server caching, the client and server cache sizes are set to 24 gig. So you are saying this is already unfair.
I'm
Uh,
saying that depending on what the clients, the computes are actually doing, right?
yeah.
Because if there is more than one compute, then it becomes
Yeah.
unfair.
Yeah. No. Oops. Okay.
Yeah.
Oh, okay. Test bed. Samsung. For Samsung.
Yeah.
NVMe SSDs. Okay. Uh, oh,
Yeah,
okay. I
yes.
I forget to say this. Cache sizes are set to 24 gigabyte and 12 gigabyte. What? Uh,
They maintain the same
oh,
36 gigabyte.
they use like three clients, or because
N-
36 divided by 3 is 12
No,
gigabyte on the server side?
no. If you have a client only cache, you put 36 gigabyte on a client. If you have server
Yeah.
only, you put 36 gigabyte on a server.
Yeah.
If you have a client and server, you split it. So 24 on the client, 12 on the server. So you still have 36 in total.
You only have one client?
Yeah, I think that's what they're going for here in the
Oh
test bed.
no. Oh
In
no.
in the next paragraph, right? Two physical machines, one client node and one server node.
Okay. Oh, like I'm disappointed. We characterize different caching, but well, easier to analyze, of course. We characterize different caching strategies with two physical machines, one client node and one server node in Cloud Lab.
Mhm.
See Cloud Lab. Each machine has one 16-core Intel Xeon Silver CPU, 128 gigabyte DRAM. See, they used Cloud Lab, not Samsung. Well, it
Yeah,
looks
well,
very
they
high.
had to say that the Cloud Lab had Samsung SSDs.
Mm. First, to understand the CPU utilization, Figure 1a shows the CPU usage for different caching approaches with different access patterns.
And table one is the access patterns, I think.
Yeah, okay, now let's look at table 1 again. Workload, random read, random write, sequential write ratio. Oh, this adds up to 100%.
Yeah.
Only one type of workload. Does this workload
I
make
don't
sense?
know.
No, it doesn't make sense. There is as much read and
Yeah.
write.
Okay.
Generally, read is like 10 times more than write generally. But
Let's
it's a competitive workload. I mean, it could stress them.
let's get to the figure 1A,
So
right? So
why single workload?
no, look. First, to understand CPU usage, figure 1A shows CPU usage for different caching approaches with different access patterns. So maybe this table one is not for figure 1A.
Oh,
So let's look at table one, figure one, I mean.
yeah, it says different caching approaches
Oh
with
no,
access
never
pattern.
mind.
Finding one, high CPU utilization on storage server, both server only caching and independent client server caching approaches suffer from significantly higher CPU. I mean, it's not suffering. You are making use of the CPU at the server. Is that a bad thing? If you don't use it, then you say, oh, it's low utilized.
Yeah.
Servers, okay, figure 1a. server-side CPU usage. I mean, if it goes, it could not go more than 100%. So why do you have 120, 140, 160, right?
Just so they can fit the legend.
Client local, server only, independent.
So what they're saying here is every time you have some caching on a server,
Sure.
it runs the server hot.
Yeah, but
Yeah.
it's not a bad thing. You like the utilization to be
Well, it is a bad
there.
thing. They have a pretty like they have the same server for the client and the server, like for the client and the storage, right? But why would you disaggregate? You want to put your storage on a machine with little CPU and little memory,
Hmm.
right?
Oh yeah,
Uh,
yeah, yeah. That's
yeah.
a good point. That's a
So you're
great
not
point.
going to have the same machines. Otherwise,
That's a
it
great
defeats
point.
the point.
And yeah, that's why I was also surprised seeing a lot of cache and CPU on the storage
Yeah.
side. Why?
Yeah. But
Yeah.
you know, the fact that they managed to consume all of their CPU from the machine that arguably is more CPU heavy than it should be, given their client, right? That's a bad thing. So I think it plays in their favor in a way. Like, you know, we have a storage machine with lots of CPU, and look, we're using all of it just to manage cache.
Yeah. As server and client, what happened to stable specialization, right?
Mhm. I think we get into 1 hour mark, so just to keep track of time.
Okay. This is because existing designs like server-only caching and independent client-server caching deploy an object store cache on the server to store data from clients, which incurs significant CPU overhead due to several factors.
Do they actually cite those existing designs that put the memcached in there?
There was a citation to memcache, but I guess it was to memcache. Let's keep reading. These
Yeah.
include maintaining a complex tree data structure to locate cache data and enforcing cache policies such as eviction requires substantial CPU resources. However, for client-only caching, which deploys caching only on the client side, CPU utilization is up to 90% lower than server-only caching. You just say that it's 10% CPU utilization at server. Although client less than 10.
It's actually 10
Very
to
low.
20 in their figures. So.
Although client local caching reduces server CPU utilization, its write performance, like that of server-only caching, is limited by the absence of a secondary cache layer to mask write-back latencies. As a result, it achieves 70% to 33% lower throughput, figure 2.1b, I think,
Mhm.
for rand write and sequential write workloads. Oh, geez, this is micro benchmark. You look at
Yeah,
each of them separately rather than and
yeah.
one workload and micro benchmarking, looking at each of them separately, and we don't see anything difference between these things, right?
No, the client local
No, no, no. I
different.
mean, no, no, no. The pattern across
Yeah,
the
yeah.
rand read, rand write, sec read, sec write doesn't change,
Mhm.
and the throughput does
I mean,
change, of course, for the rand
yeah.
write and sequential write, but basically you see same thing repeated for read and same thing for
Mhm.
write. Okay, fairness will be interesting. See, we didn't learn anything new than what they qualitatively said in the introduction. That's why sometimes I'm not big fan of the experiments unless it teaches me something new. Second, in table 1, we measure the data duplication for independent client server caching approach and Orca cache. I mean, of course, high data duplication for independent client server caching. That's the setup.
Observed, yeah,
Yeah,
up to
go ahead.
23 high data duplication for dependent client server caching. We observed up to 23.73% data duplication for independent client server caching, leading to high memory utilization. This occurs because despite deploying caches on both the client server, it lacks cache visibility and awareness between them. For
Mhm.
instance, when a client requests data from remote storage, the data is first cached in the server cache before being sent back to the client. As a result, the same data is stored redundantly in both
Is this a
caches.
bad thing? I want this actually because it makes the updates faster.
Well, okay, it depends, right? Their experiment is one client, right? So imagine I have 10 compute clients. One of them requested the data, and the data is hot across the entire
Hmm.
workload. Then the other compute clients will benefit from that cache. But in
Yeah.
their case, there is no benefit,
Oh, okay.
right? Again, like the workloads matter,
I
right?
see.
And the workloads, not in terms of just like how many reads and writes and whether they're random or not, like what happens at the kind of higher level in the application that runs on this, right? If you have a workload that exhibits some
Yeah.
hotness, right? Then you cache something at the server side because of request from one compute, and then 10 other compute nodes are going to come and ask for the same data, and it's going to be cached in a server. So you do get benefit from that duplication.
Yeah. I mean, single client setup is not realistic.
So now you will not get that benefit all the time, right?
Yeah.
But there are cases when this duplication may potentially benefit.
Okay.
Yeah.
This
So
duplication reduces the number of unique data blocks that can be stored across available memory, limiting overall performance. Again, a bit of a made-up metric, as illustrated in Figure 1b. Client local caching shows um,
yeah.
2.46 times and 1.52 times better throughput than independent client local caching for read workloads due to more efficient use of cache memory. This I don't get.
But they just say it's slow. Okay, use client only caching.
Why? I mean, why does the duplication make the throughput go down?
Because what they should have done is they should have included a cache hit ratio data here, right? Because if you have
Oh,
duplication, I think
I see. So this is a byproduct of cache
yeah,
hit.
yeah. Essentially, if you store in fewer data in a cache because of duplication, right,
Hmm,
you will have higher cache miss ratio,
hmm,
right? So that means you go to storage more often, and you suffer the performance.
okay. 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 Finding. Okay. Next in figure 1C, we present the per client throughput for independent client server caching. No, that's not 1C.
No, per client throughput. Yeah, so they have now
Oh, okay.
31 clients.
I thought this was fairness. Okay.
Oh, okay. So this is where again they lose me.
Yeah.
Per client throughput for independent client server caching, they have 31 clients. They just said that they have one server
Yeah.
with 36 gigabyte
They
per
also said that they have one client. Now, how come they have 31 clients?
31 clients times 36. That's a lot of memory too, by the way.
Or maybe through the threads they have 31 clients?
Well, they have a 16 core machine, so it's a 32 clients, right? From 0 to 31.
Yeah, but they said one client. Well, where did the...
They set one client node and one server node, two physical machines.
Yeah,
Yes, but they don't specify how many logical clients. But again, it's hard for me to like understand if the
the
yeah.
clients share caching or... How do you
Yeah,
route
yeah,
caching between them?
yeah.
Mm.
So are these 32 client IDs, which I presume run on the same server? Do they share the 36 gigabyte? Do they each have 36 gigabyte, which they physically cannot on that machine? So I guess it's a shared situation. Then it's not a very, accurate representation of what a compute node would be or client would be in that case.
Yeah, we observe significant performance imbalance across threads, where the throughput of the best performing thread can be up to
Mhm.
5.7x higher than
Yeah.
that of the worst performing one. This disparity arises because independent client-server caching lacks efficient server resource scheduling mechanisms to ensure fairness among multiple clients. As server CPU, memory, and storage resources are shared across all incoming requests, contention can lead to uneven allocation and degraded
Mhm.
performance for some clients. Given the constrained nature of server-side resources, it's crucial to implement a flexible and intelligent resource scheduling mechanism for Orca cache that can dynamically balance competing demands. Lastly, we evaluate the throughput performance of different caching strategies with different workloads. Again, different workloads to show their impact on system performance. Okay, you read.
Finds in four. Inefficient prefetching and eviction policies. Both client local caching and server only caching perform poorly due to deploying the cache on only one site. However, independent client server caching performs even worse than client local caching because of its independent cache management. Both the client, again, we read this in the introduction, really.
Yeah,
For instance, on the client side, prefetching is typically driven by file access patterns or application provided hints.
yeah.
While on server-side, prefetching operates independently based on object or block request
Mhm.
without awareness of client semantics. Again, we read this in the intro.
I'm motivated. Motivated.
Consequently, the server may prefetch data already cached. Yeah, okay. Similarly, eviction policies are uncoordinated. It's almost a repetition again.
It is redundant.
This lack of integration significantly increases cache misses and degrades performance as independent caching decisions fail. Um,
The server may evict
to
data.
leverage shared knowledge. Therefore, Orca cache should enable coordinated eviction and concurrent prefetching to improve cache efficiency.
Are you in the other page already?
Yeah, yeah. So, I
I
mean,
mean, hold on. Like, what's going on here? So this is saying that, oh, this is bad. The server may evict data still in active use by the client.
yeah, because they're
But then,
uncoordinated.
but then, if the client has it in its cache and the server has it in its cache, then that's bad.
The
That's redundancy.
yeah, if the server evicts, it's bad because the server is uncoordinated and it evicted something the client uses.
Oh,
If the server doesn't,
okay.
it's duplication, right?
Oh,
So,
but
so
maybe it should be in one of them.
yeah, yeah.
Maybe it's best
If you coordinate, I think yeah, it should be
if
in one of them.
the data is only in either client or server cache. But then be explicit and tell me about it. Okay, for design. So I guess we are going to finally make sense of figure two. Okay, goal one. Okay, we go back to requirements again. I just want to get into design. How many pages are left? Hey,
Oh,
actually, we have 2 pages left. This
yeah,
is
we get some
then
close.
why
Yeah.
are we wasting time with requirements again? Orchestrate cache management to effectively utilize. Oh no, we go to principle. Okay. Utilize memory across client and storage server and minimize related CPU overheads. Good. Um, Principle one, enable cache awareness to, let's not talk about principles like, I want to see the how. Enable cache awareness to maintain a global cache view, avoid data duplication, and reduce the overhead of frequent client server communication. Okay, goal 2, optimize server resource. Principle 2.
Adaptive resource scheduling, CPU, memory, and storage bandwidth on the server to dynamically allocate resources
Like
and ensure
the
fairness.
principles are restating the goals.
Yeah.
What's the point? Okay, goal 3, design a high-performance caching strategy for client-server caching management. Introduce flexible cache eviction policies and enable concurrent prefetching across both client, enhance caching efficiency. Orca cache design. To achieve our design goals, we introduce Orca cache, an orchestrated unified caching framework that coordinates between clients to effectively utilize available memory and enable efficient use of storage server resources. It also enables adaptive server-side resource scheduling. Uh, Figure 2 represents the higher-level design of Orca cache. First, to reduce server-side CPU and memory consumption, Orca cache exposes cache awareness and visibility to the client by shifting cache index management to client side. Okay, this is maybe, this was also mentioned in abstract, if you remember. Shifting, this delegation allows client to maintain a global cache view. If you have a single client, well, I guess it works for multiple clients. To maintain global cache view across both,
No, actually, does it?
it doesn't work. It doesn't work for multiple clients. You need another dance. But this also talked about Tango. I'm seeing less Tango so far.
If you have multiple compute nodes, right, they all have their own like local portion, but the server portion is shared, right? But who has the authoritative, essentially, index for the server side, right? It's a leadership ownership problem.
Yeah, it requires a lot of coordination.
Coordination is expensive.
Yeah. This delegation allows the client to maintain a global cache view across. Why are we talking about a single client across both client and server? Is this switching between client node and clients, or maintain global cache view across both clients, ensuring that only essential data is stored in the server cache and eliminating redundant or ineffective caching? It's a hard problem.
Mhm.
But if each client knows about what is stored for other clients or what is stored, I mean, it could broadcast it to all clients, and that could, maybe it says one-way thing from the server to clients
Yeah, I'm not sure how,
broadcasting.
how it will work with like multiple
All the time.
clients.
It could just broadcast to all clients. Specifically, Orca cache supports client-issued eviction and prefetching for the server cache, uh, which helps reduce the server CPU overhead. So this is another thing.
Mhm.
Client-issued eviction and prefetching to server. It
Yeah,
it trusts the clients a lot.
yeah. Well, again, because these clients are not like the clients of the system, they're
Yes,
clients of the storage,
yeah,
right? The
yeah, you're
compute
right.
nodes.
But even there, this could be problematic.
And they are pushing, that like compute, right? Like clients
Mm,
manage this and the clients just update the servers, the storage memory, like the
mhm.
RDMA, right? By using one-sided RDMA operations, Orca cache retrieves cache data transparently, further conserving server CPU resources. Which,
This,
it makes sense, to like put the RDMA in there and, avoid the storage CPU as much as possible because, again, like in real life, you will not have much of that CPU there. It will be like on these machines, it will be just more or less to
okay.
bootstrap all the SSDs.
Okay, the server has RDMA, right? But
Well, well,
this is the first, the storage server has RDMA.
the storage server has to be RDMA capable, yes.
First time your RDMA. And this was all first. Okay, second, on the server side, Orca Cache includes a caching service daemon that manages the cache memory allocator and system resource monitor. This daemon enables dynamic and efficient resource management by continuously tracking server resource usage, including CPU memory and storage bandwidth. This information facilitates adaptive and fair usage resource allocation. See section 3. 4.3. Finally, Orca Cache introduces fine-grained flexible cache eviction policies. I mean, we haven't. Okay, this will come. This flexible caching with support for concurrent prefetching across both the client and servers. These features enhance caching efficiency and adaptability to varying workloads. As a result, we have this Orca Cache improves overall efficiency and can improve even storage to handle higher request volumes. Let's try to make sense of figure 2.
I think the components, once you read 4.3, that figure 2 is going to be when you make sense of
Okay.
it.
Okay, yeah. Yeah, makes sense. Let's see. Oh, but I thought 4.3 was about resource allocation, but it's about components. Okay. Or Orca Cache lib.
Yeah,
Okay.
we maintain a user-level runtime library on the client side, okay? Responsible for managing the cache index and handling the network communication with the server. Similar to prior work, 1925-26, 19 is Polystore, that's fast 25. What do they have? 25-26. 25 is context-aware prefetching for near storage accelerators. That's another hot storage from last year. And 26, that's the OmniCache, we already talked about it, right? So the cache index in Orca Cache lib is implemented as a per-file range tree, where each node represents a cached data range that may reside either on the client or on the storage server. Right. To ensure scalability, Orca Cache lib employs range-level read-write locks instead of single global lock for the entire tree.
Of course.
Okay, yeah. For each client request, Orca Cache lib performs a cache index lookup. If the requested data is found on the client, it is accessed locally. Otherwise, Orca Cache lib issues a one-sided RDMA operation to fetch or update data. Because Orca Cache maintains a global view of the cache across both client and server, still don't know how, it effectively eliminates redundant data.
I mean, I guess the server broadcasts it to all clients. I mean, if there is one client, this is easy. If multiple clients, I guess every time it changes, the server broadcasts it to all clients.
Cache index is in that like user space on the client, right? So if I am writing, I'm using RDMA operation to update data directly, on the storage server. That data update, I also, the index is not on the server. I have the index. The server cannot tell others to
this
update
is
their
single
index.
clients.
It assumes a single client server at the very least, maybe multiple client threads.
You mean single client node, don't say server.
Yes. Machine. Otherwise, you somehow need to have client machines coordinate the index. You put like a put a raft in there. Or I mean, maybe eventual replication will suffice for that. If I don't know.
They could also write to the server, but this is on the client side. The server, the client, the index is on the
no. Look.
Server side.
Think about what can happen if you have a bad index, if you have stale index.
Oh, a lot of bad things can happen.
Right. So that means you pretty much cannot do anything without a strong consistency, which means you're limiting yourself to the performance of one machine regardless, or one client machine rather.
Yeah.
Yeah.
For example, during a read operation, if there is available memory on the client node, Orca cache prioritizes loading the data into the client-side cache rather than storing it into the server-side
Servers.
cache. Why would you, for the read, of course, put it on the client side? Is there any benefit having the red thing on the server-side cache? I don't see any benefit.
No, no. Look, this whole thing is okay. Let's keep reading.
For isolation purposes, a namespace must be registered during client initialization. The server creates the namespace, returns a namespace handle to the client, and records the corresponding namespace ID. Orca cache can only monitor and manage server-side cache protected by this namespace, ensuring privacy and security among clients with different certifications.
Okay, so I think now we're getting there. So if you have multiple clients, they have completely independent server-side caches as well. Like, am I understanding this correctly? If I have two clients, I need two namespaces. So on the server side, I'll have namespace for client one, namespace for client two. So now I effectively divided my available cache on the server between two clients.
And you treat
Equally, now
client,
equally,
yeah, you treat clients separately. The
yeah.
clients don't benefit from cache things from by the server for each other, and then you start thinking about, oh, the server is duplicating content because this client accesses and
Well,
that client
yeah.
accesses and
There can be like different. If two clients access the same data on the server, but they are in different like cache namespaces,
yeah.
you'll have duplication. I think. I don't know. Yeah.
I mean, the model is not clear. How many clients? How many? On the server side, server caching service daemon.
Yeah.
But
Server caching service daemon. Okay. On the server side, we dedicate specific cores to run a daemon that handles client requests. Okay. As mentioned earlier, this daemon maintains a cache memory allocator, which is responsible for allocating and invalidating cache memory. The allocator manages cache metadata table that stores essential information such as namespace IDs and device IDs. In addition, the daemon includes the resource monitoring component to continuously track CPU, memory, and storage bandwidth utilization. This monitoring enables dynamic and efficient resource management, allowing the server to allocate resources based on current demand while maintaining fairness. Okay, that's a lot of words without like any mechanisms or policies described.
mhm.
For example, in the case of memory management, the server can allocate resources as needed, but will immediately evict cache blocks, marking the data as deleted after reclamation if it detects that certain clients are consuming excessive resources and potentially degrading the performance of others. Okay? Under memory pressure, the system can also redirect client I/O requests directly to storage, thereby removing cache block allocation from critical path. Okay.
This adaptive approach also applies to CPU and storage bandwidth allocation, ensuring that resources are distributed efficiently and fairly across clients during server overload conditions. Orca cache should quickly detect such conditions and fall back to using client local cache. In our feature work, we plan to explore other adaptive strategies for dynamically switching between different caching mechanisms. Orca cache operations. We are done with the components. There are two components, the client and the server. But now figure two makes sense. See, independent namespace per client, I guess. This is one client. This is another client.
Yeah,
What?
namespace 1, namespace M, right? So there are
Yeah,
M
M
namespaces,
clients.
AIM instances of the Orca cache lib.
Right. So Orca cache lib is at the clients. That
Mhm.
they say it's on the client side. So this is like it would be useful to say that clients
Mhm.
and server, and for each client a different namespace. I mean, this dash thing down there is like a lot of you know, wish list about it's going
Mhm.
to be very resource efficient, good
Yeah.
policies used, etc. Not much concrete thing
Mhm.
on the server side. Right? Storage server daemon, two components, Orca cache lib, storage server daemon.
Well,
That's the
namespace cache.
namespace cache. The cache and the server cache index is at the client for the namespace because the namespaces are managed differently, separately, individually.
Okay, so here's a like a hot take here, right? So I still don't understand why we want caching on the server side. Like in the introduction, they
Yeah,
mentioned that
yeah,
it like does like,
yeah.
but like what does it do?
Like if you go to network,
Yeah,
get it from the flash instead of RAM.
yeah.
How much difference would it make? I thought this would be useful for maybe flashing to the storage
I
because
mean that
most
is
of
the
the
use case
content would
I
be
told you
there.
about. Yeah.
But also don't. But they don't like that much. They say that this is duplication between
Uh-huh.
client and storage, and client and
So,
server.
so I would very much would love to see at least like one example that they can provide, like where having anything on a server side is beneficial.
Yeah.
Because right now, like after reading this, like last few paragraphs, right, they're like, well, if the server is overloaded, we're just gonna like forego the server side cache and kind of just degrade it or switch it down to like client only cache.
Hmm.
So to me, like I see the benefits from having the daemon that watches the resource usages and maybe ensures that the fair resource usage in terms of like the bandwidth that they have to the storage and whatnot. But like I'm yet to see like what's the upside of actually having the cache on the server on the storage. So
Maybe this is like as in memcache. This is data presented
yeah.
in a different format, more consuming ready format rather than the
Mm,
raw format.
I don't think so.
I'm trying to
Yeah.
find uses. Orca cache operations. Next, we discuss the key operations in Orca cache. Cache operation issued by clients. The complete view of indexes and metadata for the server cache is maintained and managed by the client. One, upon encountering cache miss in the server cache, the client initiates a series of RDMA operations to retrieve the required data. Why is cache miss on server cache? Why not cache miss on the um, client side?
I guess they don't care about the client side. If you have a cache miss on the client side, that's when you go to.
Server.
Actually, you don't care. No, you don't go to server because you have an index. You know
Hmm.
whether you have local or remote. So
Yeah. Yeah. So.
right. So the local cache misses don't matter. I
Oh.
right. I mean they take virtually no time.
Mm-hmm.
Right.
And then if you notice a server cache miss, you initiate a series of RDMA operations to retrieve the required data. To where? To the server side or to you? If it
It
first
first sends a message using RDMA send to trigger the server's response. The server then transfers the data to or from the client using
hmm,
RDMA read or write and returns the memory address of cached entry, allowing the client to directly access it. And so this is talking about populating the client cache, it
Yes,
seems.
yes, that's also what I understood. In the case of a server cache hit, the client can access the data directly using RDMA read or write, bypassing the server CPU entirely. However, due to server
Resource scheduling, such as cache reclamation, a cache hit may result in a one-sided RDMA failure if the entry has been invalidated.
I don't know. In the case of a server cache hit, the client can access the data directly using RDMA read or write, bypassing the server CPU entirely.
Okay, so
However, due to a server resource scheduling, such as you are saving CPU, which is a benefit.
So number one is not about populating the local cache, it's still about populating the server cache.
Really?
Yeah.
But it says it's transferring the data to the client.
Yeah, it will transfer the data to the client because the client still needs it, but it will.
The client can then also cache it, a cache.
Reason number two then, right? Clients detecting such failure should fall back to cache miss path, which is the path number one, to retrieve the data and repopulate the server cache. Anyway, some cache will get repopulated somewhere.
If the entry has been invalidated. Result in a one-sided RDMA failure if the I mean, this is saying that if your cache hit was not a cache hit, just fall back to the cache mispath. It's not saying anything other than that. 3. Additional clients can active the batch eviction request and send prefetch requests to server as hints to improve performance. Sure, may choose to ignore these hints depending on its current resource consumption. Despite these capabilities, Orca Cache in its feature work must address challenges such as accurately inferring server side. There isn't current work on Orca Cache, so everything is feature work. Coordinating safe evictions across multiple clients and ensuring that prefetch remain effective without introducing significant overhead. Server resource scheduling. Aleksey, you read this one. We are at the end almost.
Server resource scheduling. Under high request volumes, the server can quickly exhaust memory and saturate I/O bandwidth. To mitigate this, Orca Cache deploys lightweight server-side components to manage resource usage. 4. A memory allocator monitors per client cache usage, handles invalidations, and enables fair eviction decisions. 5. What are these numbers, 4 and 5 and 6?
We were going 1, 2, 3, now 4,
I
5.
think those numbers
Operations. These are
yeah,
operations.
they are in figure 2. Yeah, okay.
Oh, yeah, makes sense. 4, 5, 6. They are not in figure 2.
They
They are
are
in figure 2. Okay,
4,
4,
5,
5,
6.
6.
See, allocate, reclaim, and
Yes. Mhm.
yeah. Um,
You know, like this whole dashed box storage server daemon is mostly wish list at this point.
yeah.
Not because there's no mechanism described. It's just saying that it does this.
Metadata for all cache entries is maintained to support memory reclamation without client coordination, preserving consistency. Okay, that's a loaded sentence, which I don't fully understand what it means. A disk monitor observes storage bandwidth and guides eviction timing to avoid interference during I/O pressure.
I mean, this
However,
is wish list, right?
yeah,
So it is basically saying, this monitor does the right thing, memory reclamation does the right thing. It's not saying anything more than that.
yep. Key challenges remain in balancing fairness and performance under load, minimizing eviction overhead, and adapting eviction time into rapidly
Okay.
shifting layout patterns.
We had read the conclusion.
Yeah. So yeah, I think it's time for our conclusion.
Yeah, okay. Okay, I'm more confused. So this is coming from a different conference than we are used to hot storage. Um,
I
so
mean,
maybe there is some things we are missing because of that, but I would have liked to see like
this is
first
not a storage paper, Murat.
contextualizing. This is like how does this relate to distributed file system work that you cited from
Yeah.
90s? Is it the same thing revisited with new hardware? Um, New workloads, but the learning workload also was not really a machine learning workload. It's just like, oh, random rates, random writes,
Yeah.
sequential writes. It's just nominally machine learning. First, like contextualize with respect to distributed file system work.
I would say like a little bit more formalism in this paper would be nice, right? Like define what the clients are, what they
Define
do.
system model, right?
Yeah,
We didn't get a system model. Um, right.
yeah. And
And you said that this is not disaggregated storage?
well, they have the experiments are one server, right? One client server,
Mm,
one storage server. So um like my concern is, like there is a lot of things in that setup that is just like too trivial, right? The client machine is the same as the server machine, right? Which means the server has
mhm,
too much CPU in relation to the clients, to the compute machines.
mhm,
There is only one compute machine, right? I mean, I think they simulate it with threads, but then I have questions about like what happens with cache. They say 36 gigabytes of cache, is it? But it's not per thread, not per like client ID. It's still per machine, which is only one machine. Um, I suppose. Um, but if that's the case, the fairness problem comes in here as well, because like, those client IDs, clients on the same machines, they share that cache in whatever unfair way possible as well, right? So um yeah, the actual like workloads, like I would love to see the examples of where these things will benefit. Right? Because in my mind, the benefit of a cache is latency, right? So I want to have the cache where I consume it, like on the compute side. If I have to go over the network, I am saving, just going to the disk part of latency, which may be like a substantial amount of latency, right? But you still pay the network,
mhm,
um, which is also a lot.
mhm,
So like what specific workloads in what specific situations can this like benefit us, right?
mhm.
Because like I don't see like they didn't provide that. I had to guesstimate like that Flushing example, which I also don't think they support
Yeah,
again because of the reasons you mentioned, right?
yeah.
So so yeah, like I'm a little bit perplexed by the need for
But
the
the thing about server-side caching, the benefit is they can access bypassing the CPU directly through one-sided RDMA. So that there is still a benefit from the server-side cache.
Yeah. Like the benefit is if you have memory on a server side that is unused, right? Then you might as well use it for cache if
Yeah,
you
yeah,
can
yeah. Oh,
if
right. No, I get
if
it.
you if you can RDMA it like that
Yeah.
that I understand. The counter argument is those storage servers,
Mhm.
they will be made so lean,
Mhm.
right? Because you are disaggregating things. You don't
And
want to.
also, right, one storage server is also very limited view of disaggregated
Yeah,
storage. We look at distributed
yeah,
storage, like
yeah,
sharded databases.
yeah,
So one storage server is also like
yeah, yeah. And that's a good point. Like, how does that client managed cache is going to be
and there is
done?
no replication, right? So one storage server, not replicated, not sharded.
I mean, I think those are orthogonal problems, to be honest. What I care about is
Not
what
replicated is not an orthogonal problem. Replication would
it is. Put it in rate, whatever, right? It's an orthogonal problem. The issue with client, the Orca cache sleep and one storage server is, when you have one of each, it's easy to maintain that index that they build, the cache, there's the
yeah,
server
sure.
cache index. What if you have, 100 storage servers that you're interacting with as a client? Are you going to have
Yeah,
an index for all of
yeah,
them? For
yeah.
every server you ever interacted, you're
Yeah,
going to start to maintain that
right.
index?
MN client server scenarios. Mm-hmm. Mm-hmm. Okay.
So yeah, I mean, like I like the introduction, right? Like the introduction read decently well, and they stated some assumptions, some problems, and
But not the thing that we thought it would be.
yeah, but then yeah, I mean, it was fun. It was fun to read. I think it did tickle my brain to think about like
Mhm.
all the other things, but yeah. I wish there was a little bit more, even in the context of this hot storage paper, at least a little bit more formally defined model of what they're trying to solve,
Yeah.
and maybe a couple concrete examples of like where that will benefit.
Okay, cool. Good news is we are 1.5 hours, I
Okay.
think. So, yeah, more than 1.5, but we are still good. Okay, cool. So I choose a paper next week and we do this again.
Yeah.
Yeah, Aleksey, take care.
Yeah.
Bye-bye.
Take care.